Hello guys, this class we are going to talk about the relational data model and its operation basis from a mathematical aspect. First, let's see the mathematical definition of a relational model. So let's see the definition of the Cartesian product. Let D1, D2, Dn be the finite sets. Then their Cartesian product is, we just write like this. So any elements D1, D2, and Dn is called an n-tuple. So that is what we called tuple before. And each Dn value, Di value is called a component. So a tuple is an ordered set of complements that make up the tuple. So if we assume the cardinal number of Di is mi, then the cardinal number of all the Cartesian products is like this. So then let's see an example. If the attributes AI, A2 takes values of Di its domain has 1, 2, 3, and D2 the domain is AB. So then the Cartesian products of the domain we can write like this. So we can see if the AI can take the 3 values and A2 can take these 2 values, then we make Cartesian products. We can got 6 tuples. So let's see another example. If there are 3 domains as follows, so men, we have these 3 men's name, and women, we have these three women, and children, we have these 3 children. So if we want to make Cartesian products between these 3 domains, we can write like this. So it's like that the Cartesian products is you just select every value from each domain and make them like make them a tuple. So basically that if you just make a Cartesian products between these 3 domains, we can get a lot of tuples. But we know that if we just make a Cartesian product without any constraints, maybe we didn't maybe the result will very meaningful will have little meaningful. So we always add some constraints on these Cartesian products. So here let's look at this table. The following are the 3 attributes. We make the domain we make the domain Cartesian products which also satisfying the family constraints. So we can got this results, and this 3 is a domain of each attribute, and this 3 tuple is what we got the final result satisfying the family constraints. Then let's see what is a relational schema. A subset of Cartesian products which it should satisfy in certain constraints. Then we call it a relation on Ni to Di to Dn. So the abbreviation is the relationship which we call a customer table. The n becomes the goal or the degree of the relationship. So when n is equal is y, so when n is 1, we call it a unitary relation, and when n is 2, we call it a binary relation. So as relation is a subset of a clustering products, so the relation is also a two-dimensional table. The relationship pattern is composed of the relationship name, attribute, domain from which the attribute comes, the attribute mapping to the domain, and constraints. So we write like this. Here, the R represents the relationship name, and the U represents the attribute name, and the D represents the domain from which the attribute comes, and this DOM represents the attribute mapping to the domain, and the final F represents to the constraints. So we write a relational schema like this. But you need to note that the relation is a finite subset of the Cartesian products. So its infinited relation is because infinited relation is meaningless in database system. Because the Cartesian products does not satisfy the commutative law, so it's like this. It doesn't satisfy this equation, but the relationship satisfies the exchange law. That is, if we change the two values, the di and the dj, we change their position. It is still the same relation. So if you want the relationship satisfies this, you need to add an attribute name to each column of the relationship. So to cancel the ordering of the relationship tuple. So in the previous classes, we have discussed several important concepts, such as catenate key. It is included single key, composited key, and all key. And we have introduced the primary key, which is very important in our database principles. And we have the primary attribute, and we have non-primary attribute. These all concepts we have introduced in the previous classes, and we have talked about the six properties of the basic relationship, which are the following these one. It including the columns are homomorphic, and different columns can come from the same field, and the order of columns does not matter, and the order of the tuples does not matter, and any two tuples cannot be additional, and the component must take the automatic value. So then let's see the relational operation system. First, let's see what is the definition. A group of operators with the relation as the operation objects and its corresponding operation rules are collectively called relation operation system. And then let's see what is relational database language. The data operation language based on relational operation system, which we call is relational database system, a relational database language. And here, any operation on the relational data model can be expressed as a relational operation expression. So then we need to know what is an operation. Here there are three elements of operation. That is operation object, operator, and operation results. So first, let's see what is a relational algebra. So the definition is a set of high-level operations based on the relationships. Each operation takes one or more relationships as its operation results and generates a relationship as its operation result. So here we can see is its operations is relation, and its operation result is relation 2. So for this kind of operation, we call it relational algebra. And here the relational operator includes the comparison operator and the logical operator. So let's see what is comparison operator. So we have these which we are always very familiar with, such as greater than, less than, and equal to. And we have the logical operator, which is not, and, or. And we also have two sets of operators, which we call set operators and the specialized relational operators, which also used in this relational algebra. So we always divided the relational operations into two categories. So it's besides the comparison operators and logical operators, we have the general set operations, which is this set operators. So it's including the union, intersection, difference, and the correlation products. And here the operation symbols are like this. And then another is the native, the specific relation operations, which including the selection, projection, connection, and the natural connection and deviation. So the operation symbols is like this. The connection is here, the selection is like this, and the selection is here, this symbol, and the projection is here, this symbol, and the connection and natural connection is here like this, and the division is here like this. So then before we introduce how to use these operators, we need to introduce concepts called operability and comparability of sites. So if the two relationships R1 and R2 involved in the operation have the same segments N, and the S attributes of relationships Ri have the same domain as the S attribute of the other relationship R2, here their attribute names can be different. So R1 and R2 are said to have compatibility and merging. So it means they need to have the same attribute and each attribute should have the same domain as another relation. So then after we know what we need to call comparable and comparable, we can just introduce how to use these different kinds of operators. First, let's discuss the operator union. So its definition is the combination of two compatible and comparable relationship R1 and R2 is a new relationship composed of all tuples T. So here we need to excluding the duplicate tuples belonging to R1 or R2 both. So the new relationship has the same set of attribute names as RE. So here we donated this union as this. So it is represents like if you make R1 and R2, which are compatible and comparable. You make a union relationship, then the result is we will get all tuples belonging to these two relationships, but excluding the duplicated tuples. For example, let's see if I give these three tables and please see what the result, what is the result of these three operations. So we can see before we merge these two, the tuples from two tables, we need to make sure if these two relations are comparable and compatible. And we can see R1 and R2, they have the same attribute and each attribute have the same domain. So we can union these two relation. We can union these two relation, and for R2 to R1, it is the same. But if we want to union R1 and R3, we can see as they have different attributes and their attributes have different domain, so we can't conduct a union operation on these two relations. So for R1 and R2, we have this result, and for R2 union R1, the result is the same, and for R1 union R3, we can't do that. It is not it is illegal. And here we can see that the result as we have the duplicate tuples, so we removed one. Then let's see the intersection operation. So the intersection of two relationships, if we want to make this operation, we first also need to make sure that these two relations are compatible and comparable. And after that, the intersection of these two relationships is a new relationship that composed of all the tuples T which belonging to both R1 and R2. And the new relationship has the same set of the attribute names as R1, and the operator which we recorded as like this. So it means that the tuples should belong to R1 as well as R2. And here we also can write like this, which we use which we can write in another format. So then let's also see this example and to see what is the result of these operations. So we can see for R1, intersect R2 as they have the same attributes and their attributes have the same domain, so we can make an intersection operation. And here this is the result, and also like the union operation, we can't do the R1 intersection R3. That is illegal. Then let's see the difference we call the manners between two relations. So if you want to make the manners operation, you need to make sure you need to also make sure the two relations are compatible and comparable. And then the manners between the two relations R1 and R2 is a new relationship composed of all tuples T belonging to R1 but not R2. So we can see R1 minus R2 is now equal to R2 minus R1. And the new relationship has the same size of attribute names as R1. So we can write like this. And then now let's also see an example how to make this manners operation. We can see if we make R1 minus R2, we want to find the tuples that belongs to R1 but not belongs to R2. So we have these two tuples. And same, we can got the similar result, but we can see these tools are not the same. And also, we can't conduct this R1 minus R3 this operation because they don't have the same attribute, and their attributes also don't have the same domain. Then let's see what is a generalized Cartesian products. Now we can see the Cartesian products of two relations are R and S, and let's R be the K1 entry relationship and S be the K2 array relation. So the Cartesian products of the two relations is a new relationship composed of a new elements group T, which T is formed by the connection of any tuple T K1 belonging to R1 and here is belonging to R and the tuple T21 belonging to S. So we donated the operator as this. We call it the Cartesian products. So it's recorded like this. So let's see an example. Also, these three tables. If we make the Cartesian products, such as we make R1 to with R1 Cartesian products to R2, so we can got these answers. So that means we have every tuples in the R1, such as A1, 2, which we need to combine to every tuples in R2. So it's like this. And then we have the next tuple, and also combine with the every tuple in R2, and then get the final result. So we can get the result that if R have the n1 tuples and S have the n2 tuples, then the product result should be n1 product n2, right? So that is the total number of the tuples from the Cartesian product results. And here we need to know that the relationship R, if it has K1 attributes and the relationship S have the K2 attributes, the principle for determining the attribute name of a new relationship after Cartesian products should be the first. The first K1 attributes take the attributes name of R and are prefixed with R. And the last K2 attributes take the attributes name of S, as it is from S, and are prefixed with S. And second, when an attribute in two relationships does not have the same name, the attribute names can be directly referenced. And third, when dealing with the product of a relationship R and itself, it is necessary to introduce the Alex for relationship R. So it is similar. It is similar with what we have learned in the SQL language writing. And here, the union intersection products satisfy the combination law of the set operation, and the manners we call it different operation does not satisfy the combination law of the set operation. Okay, so after the introduction of the set operators, we start to introduce the operations from the specific relation aspect. So with that, it's including the projection, the selection, and so on. So we start with the projection. What is a projection? It means you need to selecting some attribute we call it column from existing relationships can reorder the selected attributes and deleted duplicate rows to form a new relationship. So if R is a k-entry relation, its tuple variable is like this. And then the projection of relation R on its component like this are integers different from each other from 1 to k. So we write like this. That means we just make a projection on this R relation. So we will get all the tuples. If we want to make a projection on G1 to Gn columns, then we will get the tuples that composed of these columns, which is not duplicate. So let's also see an example. Here we have this relation we call R. The example is if you want to find the projection of relation R to A3 and A1. So you need to make a projection on these two columns. So you need to write this projection A3, A1, and here we need to write the relation R. So these two writings are both okay. Here you can just write the number of the columns is also okay. So here we got the result is like this. We got we got C1, A1, C1, A1, and C2, A2. And here because the result we have the duplicate tuples, so we removed one and finally got C1, A1, C2, A2. Then let's see what we call it a selection. So selection means we need to select tuples that meet certain conditions from existing relationships to form a new relationship. So we just write the notation like this, and it is recorded like this, which means it is a tuple that from the relation R, we should satisfy the constraint from F. So here we need the F, which means the constraints should be true. So here the F is a conditional expression, and the operation is an attribute of a constant or tuple. And here the operators it can be comparison operator and logical operator. So here let's see an example. A relation M is shown like this, and if we want to find the tuples where the A2 is greater than 4 and A1 is equal to A, here we can write like this. We can make a selection operation on the relation M with the condition that A2 is larger than 4 as well as A1 is equal to A. So here we write this and we can get the result like this. We can get the A1 is greater than 4 and A1 is equal to A. Also here, maybe we here according to this condition, we should have these two tuples, and the last one is not correct. We should remove it. And then let's see what is the seed join. We have the join. We have learned the join, different kinds of join in the SQL language writing. And here let's see how to use it in a mathematical aspect. And that TI represents is as attribute of tuple variable TKI of relation R, and TJK2 represents this attribute of tuple variable like this of S. Then the connection between two relations R and S. Here, let R be the kth elements relation and S be the K2 elements relation. So the connection between two relations R and S is a new relation formed by the new elements groups T that satisfied Tik1 seed Tjk2, which is formed by connecting any tuple Tki belonging to R and any tuple Tk2 belonging to S. So we can write like this. Which we call it a seed join. And here, if seed is equal, then we can call it a equal connection. So here, let's see an example. For these two tables, these two relations, if we want to know, we want to make a seed join between this R1 and tuple R2. Here, seed we write the condition like two greater than 2, which means this AR from this R1, the value should be greater than the A2 attribute from the R2 relationship. So we can get the final results. Here we got the relationship, we got the result where RIA2 in each tuple is larger than R2A2. And another example, if we want to make R1 and R2, which is also a seed join, and the condition is A1 from R1 is equal to A1 from R2. So the value should be equal. Then we can get the final result like this. So we can see the R1, A1, this value in each tuple is equal to R2, A1 is equal to. So that means you first make a correlation products and then select the tuples that satisfy the seed condition. Then let's see what is a natural join. And we have discussed before, the natural join is a special equal join, but it is different from the equal connection because it can automatically remove the relevant columns of the equal connections. And the natural selection conditions is like this. We can use an example to see how to make the nature connections. So we donated this nature drawing like this. Here you don't need to write the seed condition, so you just write like this. And here we can see that if we got the R and S condition, here note that I have add a new column to the S relation. And then if you want to make the nature join between R and the S, the result should be like this. Here we can see the attributes of AI and A2 from these two tables. The natural join can recognize that they are the same attribute. So in the result, it will merge these two attributes. So here we have only got one AI and one A2, and it will expect that besides that it will only join the attribute values which is equal these tuples. So the result should be A1. So we can see A1 is equal to here this E1. So we have found a equal connection. So here it is the result. And this B is the attribute value from A3 in R, and this 200 is the attribute of B from this S relationship. And then another equal relationship is C4, and here C4. So here we write like this. And here, besides this sixth join, we also have the outer join, which we have introduced in the previous classes. We have introduced the left outer join and right outer join, and here we will just leave here, and we will not discuss it in detail. And then let's see what is divided operation. So this is a little difficult. Let's see. Let Ki entry relation R and K2 every relation S, and Ki is larger than K2 and S is not. This S relationship is not empty. Then the coordinate of relation R and S is a new relation formed by a new tuple variable t after removing the same attributes as those in S from the tuples variable tk1 of relation R, which makes all tuples in the S relation tk2 all satisfy tk2 belonging to R. So we use this operator, which is denoted like this. And here is for every tk2 belonging to S and tk2 belonging to R. And the operator is denoted as assuming that the attributes of the relation S are the part of attributes of relation R. Then the result of R divided S is the attributes consist of R attributes belonging to R, but not to S, and each record is a part of R, and every tuple belonging to R divided S is taken. And after connecting with any tuple of S, it is a original tuple in R. So let's see an example. If we got a student table like this, and we have the course table, then if we want to make a division operation, which we use this table student course selection, divided course. So this table divided this table, so we can get the result is we have got the name column, and which take all these courses. That's what is the mean of the division operation. That means we will find in this example, the division means that we want to find the student which take all the courses. So we have the result is Hua Zhang which means it's this. We can see it's take math and physics both, and we have the Yue Shangli here. We have this. We can see this student also take both courses, and other students they only take at most one course, so we didn't its name shouldn't in this result. So the thinking is a student who have taken all the courses. And the definition of derivation also can represent as a concept of correlate. That means give a relation Rxd and x and z are attribute groups, and when Tx is x and the imagined size of x in R is Zx, so it represents the set of components in Z of tuples whose values is x in the attribute groups x in R. So for example, if we have these three attributes and the imagined size Z, and in each relation R, A can take four variables A, AI, A2, A3, A4 here, and we can see B can take these three combinations, and A1 are these combinations. We can see A1, it can be B1, C2, B2, C3, and B2, C1 here. And the A2 is the imagined side of A2 is B3, C7, and B2, C3. Here we can see this and this. For example, we have got all this image side of all the four values. And then give the relationships Rxy and xyz, where the xyz are the attribute groups. Then y in R and y in S can have different attribute names but must from the same domain. So the definition operation of R and S is a new relation Px, where P is the projection of the tuple in R on the X attribute columns, which satisfies the following conditions. The tuple in X, the image side Yx of the component values X contains S in Y, and a connection of upper projections. So it's like this. Here the Yx is the image side of X in R, and X is equal to, here is equal to TRX. So here you can just acknowledge that, and we don't require you to just know how to get the result using the imagined site. So we can see these are the R relation, and this is the S relation, and R divided S, which we need to know, we need to find the values which have the imagined side like this. So we can see here which we got like this. So the imagined side which satisfies this S is A1, only A1. So we got A1 here. So the division operation is performed from both row and column perspectives. So we can see if you want to make R divided S, so we can got here like this. And then we can see the implementation of 5 basic operations. So for these basic operations, such as attribute subdivision in relation, it is corresponding to the projection like this. And for the tuple selection in the relation, we have the selection notation. And the merge to relationship, we have the product relation. And in insertion of relation tuples, we have the merge. And deletion of relation tuples, we have the manners. And here I have listed several conversion of relational operator to SQL. So here we can see that the select symbol is similar to where in the SQL language, and the project symbol is similar to the select in SQL, and union symbol is similar to the union in SQL, and manners is equal to, and the Cartesian products is corresponding, which is similar to the inner join without condition in SQL, and the rename we write like this is similar to as in SQL, and the intersection is similar to the intersection in SQL, and the nature join, which we write like this, here is the seed join is similar to the inner join in the SQL. So that is the operations which we used in the relational model. Then let's come to the second part, the relational systems and query optimization. And first, let's see what is relational systems. It is a database management systems that support the relational model. So we need to, these relational systems should support the relational data structures. It should support the relational operations such as selection, projection, and join. And here the physical access paths are transferred to the users. So it should satisfy all these conditions. So we can call it relational systems. And here we have these 4 kinds of systems, and we can see this one is we can see here we have the 3 chapter, and S represents the structure, and M represents the manipulation, and I represents the integrated constraints. So for the first, this one, it only have the structure, we call it a table system, and as it cannot have any relational operations, so it is not a relational system. We call it a table system. And here, this one, we have the S and M, these two, and we call it a minimal relational system. And here we have this one, we call it relational complete system. And this, we have all these three functions, then we call it full relational system. And the guidelines for the relational system, including relational DBMS, must be able to manage the database entirely. Its root is relational completeness. And the information calculation is that all the information is explicitly represented at the logical level with values in tables, and guaranteed access criteria according to the combination of table name, primary key, and column name, and each data item in the relational database can be accessed logically. And systematic handling of non-values. It is supported for none. It should support it for nine. And the dramatic online data dictionary based on relational model. It is storing the metadata in the relational form. And unified data sublanguage guidance. It is the unified data sublanguage. And also it should have the view update calculation, which all the semantically updatable tabs should also be allowed to be updated by the system. And also it should have advanced insert, modify, deleted operations. And that means operations on the relationships. And we have the physical independence of data and the logical independence of data, and the independence of data integrity, which is defined in data definition language and stored in the data dictionary, and not application defined it. And the distribution independence is should allow that the data distribution does not affect the application. And final is the non-branch calculation, means low-level language cannot bypass the integrated calculation. And then let's come to study the query optimization for relational systems. So when we write the SQL language, we only focus on what to do and what result you want to query. And the DBMS, it stops how to do it and select the access path of the query. So for query processing steps, we have the query analysis, which including the sentence scanning analysis and explanation and mapping, so on. And we have the query check, which it will check the semantics and the permissions and check if it is satisfy the integrated constraints. And it will convert it to the equivalent relational Algebra expressions. And then we have the query optimization, which we have the algebraic optimization and physical optimization. And then we have the query execution, which just generated the code and process the query. And here's the query optimizer for the DBMS. It's including leverage the statistic from the data dictionary and the geometric optimization with database changes, and construct a large number of query plans and choose the best from them, and then use the sophisticated optimization techniques. And we have the query processing, which during the query processing, it should analyze and interpret the query request and generate a query plan, generate just a set of query plans. And the query optimization is aims to find the best query plan which has the shortest processing time. And the optimal, which we means it is the least expensive, so we will consider the disk I/O and the CPU running time. And here this is the DBMS and the query. You see we have this query here and into the DML comparator, and here it can have it will analyze the query. It will generate the query plan here. This we all called a query processor, and we Here we have the DML comparator, and we have the embedded DML pre-comparator, and here we have the query evaluation energy, which will generate the query plans for this query and will select the best plan according to the cost evaluation, and then process the best query plan and get the result. And the process of query processing can be concluded as first, the users makes a query, and then the query processing will first conduct the phrasing, which means convert the query into a equivalent internal representation, which we call it a semantics tree, and the equal transformation into the optimized semantics tree. And we will choose the underlying algorithm for each operation in the semantics tree and generate multiple query plans and calculate the cost of each query plan and select the query plan with the latest cost. And finally is execute the query and return the result side to the user. So a query optimization example is to find the name of the student who took course 2, which like this, we will write a SQL language. And here is you that the number of students is 1,000 and the grade result is 10,000, and the number of people who took the courses is 250. Then the general strategy for the query optimization is that first you need to choose to do it first. Choose what to do first, and you need to processing before the connection. So we will have these two solutions: index or sort, and we have the select and projection merge. And we have the projection combined with other operations, and we have the select and the condition integration into join, and we have the common sub-expressions are evaluated only once. So this is the general structure which may speed up the query processing. And if you want to determine that what to process is maybe more faster, here we have concluded the equal transformation rules for the relational algebra. So we have the exchange rate of connection Cartesian product, and we have the associativity of connections or Cartesian products, and we have the concatenation law of selection or production, and we have the selected exchange rate with projection, and we have the truth exchange rate with Cartesian product, and we have the choose the exchange rate of and difference, and we have the projection and the Cartesian product or Yunnan swap. So here I just list these rules here, and I won't just explain it in detail. And here let's see, I have give an example to see how to phrasing the queries. First, let's see variance equal relation algebra expressions. You can see these three writings are equal. Right, you can see these three writings are equal, but their costs are different. Suppose there are 6 memory blocks and each block can hold 10 student tuples or 100 grade tuples and read and write 20 blocks per second. So issue 5 blocks hold student tuples and 1 block holds the grade tuples. Then we have for the first writings like this, we have these correlation products which is cost like this. Cost like this, and then we have the time is like this. Which is including the time of read and write. Then after the correlation products, we have the select time. So here the select time is read. We have cost 50,000 seconds. And then we have the projection time, which can be ignored. So the total time cost is this one plus this one plus this one. Then let's see the second let's see the second writing here. The natural drawing, which read is 2,100 blocks, which may take 105 seconds, and we have the write, which need 1,000 blocks and 50 seconds, and we have the select here. The read may be 50 seconds, and the projection here can be the null. So the total cost time is this one plus this one plus this one. So we can see it is much faster than this. And then let's see the third one. First, you need to select grid, and so this one is the read cost, and the result is in memory. And then you need to read the connections with the student table. So we have this cost, and then we have the projection. So we can see this solution is the fastest. It is cost the latest time. So if there is an index on CNO on the grade table and an index on SNO on the student table, there is no need to perform a full table scan, which will be more efficient. So here, as we know, the writing, maybe we can get same result, but the cost is different. So that is why we need the query optimization. So here, for example, we have write a SQL language, and these two tables schema is like this. So we can see these two selections. We can get it's equal, which means we can get the same result, but their cost is different. For example, if you want to first make a correlation, first you need to make a nature drawing between these two tables, and the cost is like this. And if you first select the class name, this one, and you just after select the name and just projection got the cast number, and then you make a nature drawing with this reserve table, then the cost is like this. The cost here is 3,000, which is here, and the cost then the total cost of the nature drawing is 10,000 plus is 10,000 plus the 30. And here, if you first make a nature drawing, the cost is 10,000 plus 3,000. So that is larger, very larger than this one. And then after the query optimization of this phrase tree, we have the physical optimization, which means we select an efficient and reusable operation algorithm or access path and obtain an optimized query plan and achieve the goal of query optimization. So here we have the circle and the relational algorithm. Here we have the selection, projection, join, and we have the set operations and other. And for the query optimizations, we need the information, or we need to take advantage of this information, such as database statistics and query statistics and index information and algorithmic manipulation and join strategies. We are here. The nested loops, the sort merge, the index-based, the hash-based. These are the physical strategies. And here, why we use the index information? That is because the indexing helps to reduce the I/O time. What is the circle definition of the integrated constraints? The core objects of this class is master the concept and the function of integrity and master the definition of the three types of the integrity in our relational database systems and their circle implementation methods. And the constants of this selection is we are going to talk about the classification of data integrity constraints, and it includes what is the data integrity and the circle implication about the data integrity constraints, and also about how to update each constraint. And first, let's have a quick review of the related content. And we have talked about the three elements of the data model in chapter 2, and we have discussed about a data model. It has three elements about the data structure, data manipulation, and data integrity constraints. And about the data constructor, for example, for a relational database, we have studied how to define a table, a database, and for the data manipulation, we have discussed how to query, how to make queries on the tables, and how to update, how to insert, delete, and select data from a lot of tables. And in this class, we are going to talk about how does this data integrity constraints can make our data in the database very safe, very complex. And for this tool, it's going to corresponding to the basic usage of the circle statement, which we have learned in chapter 3, and we can see that for the definition of data structure, we have learned how to use the DDL. It's about data definition language. How to use the created table, alter table, drop table to make this statement to construct a data structure. And for this data manipulation, it is corresponding to the DML statement, and we have learned how to select, insert, update, delete data in the table. And we can see that the data model should provide the means to define and automatically check during the manipulation. So that's why we need to learn the data integrity. And first, let me give you the definition of the data integrity. The data integrity refers to the correctness and compatibility of the data. And we have these two solutions to prevent illegal data from entering the database. And in the application, the first one is in the application, we need to add check code for each insert, update, and delete operation. And the second one is the database management system. They will use a certain control mechanism to check whether the stored data meets the specified conditions, and these conditions we call it integrity constraints. And we have the classification of data integrity constraints. It's about the column, it's about the tuple and the table, it's also about the constraints among multiple tables. So we have several kinds of data integrity constraints. And recall that we have discussed, we have introduced the integrity constraints of relational model. It is about these three. It's about the entity integrity, it's about the referential integrity, and we have the user-defined integrity. And let's see, for each integrity, we have several SQL implementation methods. For example, for entity integrity, we can add primary key. We call it primary key constraints, and we can add not non-unique when you created a table. And in this way, we can keep the entity integrity. We can keep this entity integrity, and we can see that the not non-unique it is a kind of unique constraints which can make the column the data in the column is not duplicate. And for the referential integrity, we can add foreign key constraints, and we can use the trigger constraints. And for user-defined integrity, we always use these check constraints and default constraints and trigger constraints. And we need to know that for the former two, the check constraints and the default constraints, these two are static constraints, and this trigger constraint we call it dynamic constraint. And first, let's see how to make this constraint implementation in SQL language. First is the data integrity and primary key. And we have introduced before that for the data integrity, if an attribute A is a primary attribute of a relation schema R, no tuple complement in A can be empty. So the definition of this master code in the DBMS can ensure the entity integrity. And we know that for the primary attribute, we call it, it refers to the attributes that contained in any candidate key, and this kind of attribute, it should not be none. And for the implementation in SQL language, we can see that we can use the created table statement. And for example, we can add the keyword primary key directly after the column name. For example, let us see if you want to create a table employee. If you make sure that the ENO should be the primary key of this table, you can add a primary key just after the definition of this column. So it's about add a description to the end of the column definition of the create table statement. And if for the case that the primary key is made of multiple attributes, then you can use another writing solution. You can use the primary key writing here at the end of the definition, and you can use the multiple attributes just inside here, one by one. So these are the two types of the definition using primary key to ensure the entity integrity. And there is also a solution that if you don't want to create a primary key during the created table process, then you can use this alter table statement. So you should write the alter table name and then add primary key and to this specific column. So you write column name list here. And for example, if we want to add a primary key ENO, these two attributes as the primary key to the item employee table, we can use this SQL language alter table item employee add primary key ENO. And here we need to know what's the difference between the unique constraint and the primary key constraints in terms of their foundation and definition methods, and how to do the unique constraints related to the primary key. And first, we need to know for each table, we have several types of candidate key, and each attribute belongs to any candidate key. It should not have tuples to be duplicated. So for each attribute belong to any candidate key, you should give them unique. But for each table, we have only one group of primary key. So that's the difference. That is for a table, we can have many types, many groups of unique constraint, but we only have one primary key constraint. And if you want to, and for the candidate keys, you can use unique and not none to constrain them. And for the unique, it allows not line. It allows empty. But for the primary key, it don't allows empty. It should be not none. And second, for the relational integrity and foreign key, we can see that. So for these four situations, we have talked about that if for a parents table where it's a references relationship, for example, for the employee table, we have the DNO, and that is department number. This attribute, it is a primary key of this table. So it should reference the DNO attribute of the department table. So for this kind of referential relationship, we have these 4 conditions that is not suitable for update. For example, for the first one, if we want to insert a record in employee whose DNO value is not none, but does not appear in the department table. So this is not correct, right? And for these 3 conditions, it is also this kind of thing. The second one modifies the employee's record with the new DNO's value, which is not none, but it is also not appear in the department table. So it is also not correct. So for these 4 situations, in order to deal with them, we need to set this referential integration between the 2 tables. So it's between the parent table and the subtable. And the attribute or a tuple F of the table R refers to the attribute A of the table P. So we write like this. A is P's primary key. So the value of the RF should be, or you can be equal to the medium value of the PA, or you need to take a non-value. So we can write this kind of reference integrity to keep these 4 these 4 conditions do not appear. So for the SQL language, we can define this kind of reference constraints like this. For the item employee table, if you want to define this referential integrity during the process of creating the table, you can write like this. First, you need to define a table and the table name and the table's attribute, and we set the UNO and INO as the primary key. And as the UNO and INO is also the foreign key of the employee table and item table, so we write this foreign key UNO references employee UNO and foreign key INO reference INO items INO. So this is the usage of the SQL language of the referential integrity. And to implement the strategy for the referential integrity constraints, we have these 3 types. First is the restraint. It is the default strategy for the SQL language, which is suitable for the above 4 situations. And we have the cascade option, which is suitable for the later 2 situations. And also we have the not none, which is suitable for the later two situations. And for the later, these 2, they have the difference is that for the cascade, if you write this kind of option, it will make these two records not appear. And if you want to delete or modify the record in this table, then the corresponding value in this employee table will be updated, will be deleted or modified the same as the value in the department table, which is we call the cascade. And for the set none is that if the parents table, the primary key column in the parents table, it needs to be deleted or modified for our employee table, their attribute value should be, we will set it as none. So it is not keep the same as the updates. So these 2 options are not the same. And for these 3 strategies, we have on delete, on updates, these two you can choose. And here we need to know that for the oracle by 8i, it only supports cascade to on delete expect for restrict. And for the SQL Survey 200, it supports the updates and delete cascade. And here I also give several examples. And we can see the first one is, or we talk about, we can add this two foreign key to reference different tables. And we can write on delete cascade to make this option clear. Here we use cascade means that if the values in this parents table, this employee table, the ENO is updated, the ENO in our atom employee table should also be updated. And we write on delete cascade means the values in ENO, if it is deleted, so the value in the ENO of our table atom employee should be deleted too. And for the foreign key, INO references items INO, it is the same thing. And we can also use alter table to add this kind of foreign key here. We can use alter table employee, add foreign key, DNO references department DNO. And here we can write on delete cascade, which is the same with this one. And we can write on update set none. And this means that if the value of DNO in department is updated, then the corresponding value in our employee table, this DNO, is set to none. And here there is a question, can the foreign key be set to set none here? And here we can see that here we can write the foreign key, we can set to none, but here we can't set this foreign key DNO to none because here we have this update set none option. And the third one is the user-defined integrity and default and check. And here we should first describe what is a user-defined integrity. And it is also depends on the needs of application environment, and is semantically related. And we also use several methods such as not none, default, check, trigger, and accession, and so on. And here we just introduce the check and trigger, these two solutions. And for the first one is the check constraints, and how to use these check constraints to be a user-defined integrity constraint. First, for these check constraints, these constraints can be any clause that appears in where. So therefore, it has a very strong impressive ability, and it is also used for range constraints of data. For example, if we want to check the attribute of sex, if its value is in the domain of male and female, we can use this kind of check constraints. So you can write this kind of check constraints just after the definition of this attribute. Now here we use the default, which means that if this sex you set is none, we give a default value M. it represents male. And for the age, we need to check we need to keep its domain in a given range. So we can write a check constraint here. Means age, we give an int type, and the check constraint is this age is larger than 16 and is smaller than 70. And apart from this kind of column constraints, which is constraint on a single column, we also have this kind of tuple-based check constraints. So it is constraints on tuples, which always on multiple attributes, multiple columns, and it is also similar to column-based check constraints. So let's see these two examples. First, we can use this check sex is equal to female or name is not like MS. So this check constraints means it is either it is a female or its name does not appear MS. This MS does not appear. So we can see that this kind of constraints is constraints on multiple attributes. It's constraints on sex as well as name. And for the second one, this kind of constraints, it is the same. We add a check which this constraints is related to two attributes. It's related to insure and base pay. So this kind of constraints, we call it tuple-based check constraints. And it says the employees provident fund cannot be greater than 10% of their basic salary. Okay, so after the description of the definition of check constraints, we will introduce how to modify them. And first, you need to name these constraints and then add or delete them. So the format is that constraints and as the constraint name and the constraint definition. For example, these three are all constraints we have defined. And after the definition, we can use alter table name, and add constraint name, and constraint definition to add a constraint for this existing table. And we can also use drop to delete the existing constraints from tables. So it is the function of delete constraints. And here, let's see another example. Here, we can see that I wrote a department number chart tool and it references the department DNO. So it's references the department table and the DNO attribute. So if you don't want to make these references constraint during the process of created table process, you can also use alter function. So after the definition like this, it is a very normal definition. You can use alter table employee add constraints, add a new constraint. We call it FK department, and the foreign key. We need to use the foreign key. DEMPNO references the department's primary key DNO. So you can also use this kind of you can also use this kind of you can also write this kind of SQL language to add a constraint after the creation of a table. And then let's begin to talk about the triggers in the SQL language. And the content in this section includes the introducing the triggers and how it is including how the triggers work and how to define the triggers and the triggers example. First, let's see the function of the triggers. Issues we have these two tables, and we want to insert a new tuple like this, and we have a new tuple of the salary, which corresponding to this this new record. So we can see that if we know the salary of this new record, we can just have a constraint on the title of this new guy, because we can see a new guy which has a salary which is not very high. We can assume that his title is not very high. So this is a constraint which we can use triggers to achieve that. So the composition of a trigger, we have a trigger event and the action that triggers execute. So the tab includes the insert trigger, the update trigger, and the delete trigger. First, let's see the temporary view produced by trigger. First, we have this kind of definition. We define a column 1, int primary key, and column 2, we have the char 10. And if we want to make an insert action, we insert this test table values 1, and first, it will have, if we have an insert trigger, it will just record, it will have a table which we named the inserted table, which we record here, and we have an inserted table. And for the update event, if we want to update this test table, which we set, the column 2 should be the second when the column 1 is 1. So if we want to make this kind of update, the update trigger will keep these two kinds of tables. The first is inserted table, which is the new table, the new tuple we inserted, and this one is the old tuple we just deleted. So what is a trigger? A formal definition is that a trigger is a special SQL program that automatically triggers the execution when performing the update, insert, or delete operations on a table or view. So the function of the trigger first is called in the response to an insert, update, or delete event when the data in the specific table changes. And the second one is enforce the business rules. So then let me introduce the working principle of these three triggers. First is the working process of the insert trigger. So if you want to set an insert statement to a table with an insert trigger defined, it's like this. Insert, we have order details. Insert to this order details table with a new record like this. Then for this table, we have inserted this new record, and the insert statement are logged to the log here. So it's an inserted table. And it will execute the trigger action. This action is if the order details table it has insert a new record, then we need to update the table P of what? Of set the attribute of units in stock should be the P. P is that should be the P is the products table. So this one, So this user units in stock should be the the old one. Add the new one. Add the new one. This I should be inserted. So the inserted is this table. So this table's quantity should be 5. So 5 plus 10 should be 15. Should be 15. So this one I have made a mistake. It is should be a plus. So this is a execute trigger action. That means if you made a update, you made a insert, you made a insert action to this order details, it will trigger an action that it will update the values in a products table. So let us summarize the whole process of an insert trigger is that first, it will set an insert statement to a table that defines an insert trigger. And second one is the insert statement is recorded in the log and then will execute the trigger action. And then let's see the working principle of the delete trigger. First is the send a delete statement to the table where the delete trigger is defined. First, for this delete language, which we want to delete this record, where the category ID is equal to 4. So we will remove this record, and we will log in the delete statement in the deleted table, and then we'll execute the trigger action. So this trigger action says that if we have make a delete action to the categories table, we will update the products table. We will update the products table, the discontinued attributes value to be 1. So we know that we can make an inner join from the products value and this deleted table. So if we want to delete the category ID is 4, we will delete this one. And the products ID and the discontinued value we can set it to 1. So if we issued for this product ID is 2, this attribute which refers to the category ID is 4, then we will set this discontinued value to 1. So the working procedure of the delete trigger should be set a delete statement to the table that defines to the delete trigger, and then log the delete statement, and then execute the trigger action. And then let's see the working procedure of the update trigger. First is set an update statement to the table where the update trigger is defined. So here, let's see, this is update SQL language, and it says we need to set the employee ID to 17, where the employee ID is 2. So we need to change this 2 to 17. So what recorded, which recorded in the log, as we will use this 2 log to just log this insert and delete statement. So the update statement will divide it into these 2. First we deleted the old tuple and then inserted a new tuple. So it's the process of the update statement. So then let's execute a trigger action is that if we update the records in the employees, we will have a trigger says that if you want to update the employee ID, we will says that this transition cannot be processed. So it means the employee ID number cannot be modified. That means you can't, we use this trigger to make sure that you can't revise the employee ID in the employee table. So the procedure is to send an update statement to the table that defines the update trigger and recorded in the log as insert and delete statement as an update statement, and then execute the trigger action. And then let's see how to define the trigger. First, how to create a trigger. We need to have permissions are required. And we can contain several statements. So let's see, this is a trigger to use a test. So it says if you have delayed a lot of tables which is larger than 1, then it will say that it will have an error that reported you can't delete more than 1 distributors at a time. So it will not allow this kind of deletion, which is more than two tuples. So the grammar is created the table name and the created trigger. Then you give a trigger name and the table name for insert. For example, for insert, then you write a as. Here follows a SQL statement. So the example will be you can create a trigger named student insert, which automatically updates the names of students in the class table when the user inserts table in the student table. So here you can just practice to write this kind of trigger, and I will give the answer in the next class. And here, let's see how to create a delete trigger. So the grammar is similar to the insert, and you can just replace here the insert to the delete. And here we also have you can also think about how to create a trigger named student deleted, which automatically updates the numbers of students in the class table when deleting the records in the student table. So here you can just think about how to write this kind of trigger. And then let's see how to create an update trigger. Here it is also the similar. You can just use an update to replace the insert or delete. And here you can also try to create a trigger named TA update, which automatically updates the numbers of teachers in the department table when the data of the teachers table is updated. And then after the creation of trigger, you can also update it. So you can just modify the definition of the trigger without delete it. And the triggers can also be disabled or enabled. So here we can see that you can just change the definition from 1 to 2. So you can, by doing this, you can update this trigger. And here we also give the solutions of view and delete triggers. So for view triggers, you can just use this kind of functions to commands to do the corresponding functions. First, if you want to view the trigger information in the table, you can write sp have trigger table name, and also if you want to view the definition of trigger, you can use have sp have text trigger name, and if you want to view in the dependency of triggers, you can use sp depends trigger name. And if you want to delete the created triggers, you can use draw trigger and add the trigger name. Here we also provide how to manage the triggers. First, you can use the alter table, the disable trigger to disable it. And you can use this, you can also use this to receive the use of trigger that enable trigger trigger name. So you can just refers to the SQL Server. We have the system object system table, which is displayed in the trigger. So here you can see that we also give a example of a trigger on this product tables for update. So here we can see that it is example. It is an update example. Here you update this column, this tuple. If you update this tuple, then it will let you to delete the corresponding tuples from the back orders. So this is also example of trigger for update. And here you can use these triggers to manage the. You can use these triggers to reinforce these business rules. So here, if we want the products with outstanding orders cannot be deleted, we can use this kind of SQL language. So if we want to delete these tuples, it will use the trigger code to check the order details table here. And it will find that this transition cannot be processed because these objects has order history. So it will roll back the transition, which will not allow you to delete this record. So it will appear here. It means you can't just delete it. So the summary of this session is, first, you need to understanding the role of triggers, and you can just know the method of creating and managing triggers is okay. So it is the whole content of this class. Thank you.